Hey class, welcome back. I have another example problem for you. This is a tricky one for sure, and it's looking at work being done by a variable force. So what we're told is we have a figure here. This figure shows the acceleration of a 2 kilogram package as a function of position. All right, and so we're told that AS, this point up here, is 6 meters per second squared. We're told that it starts from rest, so V initial is 0 meters per second. And we're asked a series of different things. A asks us how much work has been done, when you're at the 5 meter mark. B asks us how much work has been done once you reach the 9 meter mark. Okay, and then C asks us what our speed is at the 5 meter mark. And D asks us what our speed is at the 9 meter mark. Maybe I'll rewrite some of this because it's a little sloppy, but 5 meters and 9 meters. Cool. So the question then is, well, what are we going to do? So we know that work, right, if we just kind of wanted to remind ourselves, we know that work is equal to the integral of force times dx, right? And so integral, again, is area under the curve. So the work done, let's say the work done in the first 5 seconds, or in the first 5 meters, is going to be the area of this section here. This whole thing here is going to be the work done in 5 seconds, and then the work done in 9 seconds, right, that's going to be all of this and all of this area together. All right, so that's what we're looking at here. Now I want to erase all of that so that I can use this drawing some more, but anyway, that's the work that we're talking about. Okay, so let's go ahead and jump in getting started. So let's start with part A. We want the work done in 5 seconds. So what that's going to be, work is going to be equal to the area under the curve. But the area, this is acceleration and displacement, right? Work is force times displacement, right? So the work is going to be equal to the area under that multiplied by mass, because force equals mass times acceleration, and so work is going to be mass times acceleration multiplied by your distance or displacement x. Okay, so maybe I'll replace this over here with an x. All right, so we want to take the area, multiply it by the mass, and that'll give us what we're looking for. So the work for section 5 is going to be equal to the mass multiplied by, let's break this into parts. So let's call A1, let's define this here as A1. I'm just going to color coordinate it here for you, plus the area 2, which that we can describe as this rectangular section here, and then plus A3, which would be another triangular section right here. All right, so all of that then multiplied by the mass is going to give us the total work. So let's do that. So the work in the first 5 meters is going to be equal to our mass, which we know to be 2 kilograms, multiplied by our different areas. So our area 1 is a triangle, so 1/2 base times height. So 1/2, let's see, 1 meter is the base, multiplied by the height of 6 meters per second squared. So that's A1. And then we're going to do plus A2, which is just a rectangle. The base, let's see, we got 1, 2, 3. So 3 meters multiplied by 6 meters per second squared. And then lastly, we're going to add the third area, which is going to be, let's see, again, 1/2 1 meter times 6 meters per second squared. So that's actually the same as the first one. Cool. Oh, that's supposed to be in parentheses. All right, so if we go ahead and do the math, let's see, here we got 3 plus 18 plus 3, so 3 plus 18 plus 3 gives us a total of what is that, 24 joules? Just kidding, so that's what's inside. Okay, let's just erase this. All right, let's go back. Mental math is your friend. All right, so what that gives us is we still have our 2 kilograms, and then inside the parentheses, the area is 24 meters times meters per second squared. Okay, so now what we're going to get for our work during the 5 meters is going to be a total of 48 joules. That seems better. So boom, that is most definitely box worthy. So that's part A. For part B, I think I'm going to move off to the side over here because I need the graph still. So what is the work going to be done? So part B, we're now looking at the work done in the first 9 seconds. So that is going to be equal to the work done at 9 meters. I keep saying seconds, sorry, 9 meters. That's going to be equal to the work done during the first 5 meters plus the work done between 5 and 9, right? So since we already know the work in the first 5 meters, we just need to figure out this lower area section, and then we'll add them together. So let's work on that. So the work done from 5 to 9 is going to be equal to, again, we're going to have 3 different areas. So we can call this area 1. So this is going to be, oh, we're below the x-axis, so we're going to have negative accelerations, don't forget. So you have 2 kilograms multiplied by area 1 plus this guy here, right? So area 2, and then plus area 3, once again, which is this area here. All right, so let's go ahead and work that out. So the work done from 5 to 9 is going to be equal to 2 kilograms multiplied by A1 is going to be 1/2 times 1 meter multiplied by, now we're looking at -6 meters per second squared. And then we're going to have the blue one, which is going to be plus. Now this is only 2 seconds wide, right? So we have 2 meters wide multiplied by 6 meters per second squared. And then we have, oh, boy howdy, I almost forgot, that's negative still. Don't forget, negative. And then we have plus another 1/2 1 meter multiplied by -6 meters per second squared. And all of that deserves an in parenthesis. So let's again do our math. So our work just between 5 and 9 is going to be equal to, so we have 2, and then let's just write it out, 2 kilograms multiplied. So we have -3 meters times meters per second squared, -12, -3. So we're looking at a total of -18 meters times meters per second squared. And so if we calculate that out, multiplying by 2, it should become -36 joules is the work done. And so if we want to find our total work done during the first 9 meters of this force being applied, that's going to be equal to the 48 joules from the first 5 meters minus the 36 joules from meters 5 to 9. And so the total work done in those first 9 meters should come out to be equal to 12 joules of work. Oh, boy howdy, box worthy, right? Sweet. So we now have our answers to parts A and B. Now we have to move on to part C. Part C asks us, what is our speed at the 5 meter mark, right? Oh man, how are we going to do this? Well, work energy theorem. Work equals change in kinetic energy, right? So that means 1/2 mv final squared minus 1/2 mv initial squared is going to be equal to your work. And since we start from rest, what we have is 1/2 mv at 5 meters squared is going to be equal to our work at the 5 meter mark. And similarly, for part D, we're going to have 1/2 mv at 9 meters squared equals the work done over those 9 meters. So to solve for V at 5 meters is just going to be equal to the square root of 2 times the work divided by the mass, which also happens to be 2. So 2 times 48 joules over 2, we have the square root of 48. So you plug and chug, the square root of 48, I believe, is just a tiny bit less than 7, 0.93 meters per second. Oh, box-worthy once again. And then over here, we have the same thing. Velocity at 9 meters is going to be the square root of 2 times the work over the mass. So we're looking at, once again, the square root of 12. So the velocity at 9 meters is going to be about 3.46 meters per second. Once again, box-worthy. So that, my friends, is quite the example problem. It's a tricky one, very colorful as well. But anyway, yeah, I hope that helps. Let me know if you have any questions, and have yourselves a box-worthy night.